welcome Walter in the sky and online people and over in the room. Today we'll be hearing from John Bertram. John is currently a faculty member here at the University of Calgary with appointments in the Cumming School of Medicine, Veterinary Medicine, and the Department of Biomedical Engineering. John's academic career began at the University of British Columbia in the zoology department, where he specialized in ecology and physiology. He then completed his master's in biomechanics, where he conducted a project on horse hoof material properties. From there, John earned his PhD in comparative biology at the University of Chicago, advised by Dr. Wiener. His PhD project was on the structural form of bones and trees. John completed 2 postdocs, one at Dalhousie University and one at Harvard University. For 6 years, he held a faculty appointment at Cornell University in the veterinary department. And for another 6 years, he held a faculty appointment at Florida State University in the College of Health and Human Sciences. John's research interests include terrestrial locomotion dynamics of people and animals. His proudest scientific accomplishment is explaining the dynamics of horse gallop. A fun fact about John is that his most enjoyable pastime is canoeing. So first have John give his presentation, and then for the question and answer, we'll watch any in-room questions and the on-Zoom questions.
Thanks very much, Emily. Yeah, one of my pastimes is canoeing, but those that meet me in the bar know I've got other pastimes as well. So we all.
Hey, John, just one second, please. Just 1 second. Hoa, can you make the maybe a little bit louder? It seems to be fairly low, the voice. It's kind of hard to understand.
Yell talk with me.
Okay, so try that. Can you hear us clearly?
Does that work, Walter?
Yeah, we hear you. I think it's still a bit low, but that's loud.
Okay, how does that sound?
That's perfect.
Okay, great. And I'll try and stick in this spot so I don't get near the speakers to get crosstalk. Okay, we've all recognized the difference between walking and running. It's fairly obvious, but I suspect that for the last 5 or more years, every grant application I've had starts off with walking and running are very well described, but they're not well understood. And so the objective of my talk today is to relay a little bit of understanding about walking and running that I've come across over my time investigating locomotion. And these were, in many cases, surprising similarities and differences between walking and running that helped me explain why these gaits were effective. So why gaits at all? A gait, the definition that I like, is a distinct periodic mode that results in progression through the environment. And I emphasize environment there because legged organisms aren't the only ones that have gaits. Birds and flying insects have flight gaits, and fish have different gaits, and even reptiles that swim through the sand have different gaits. So it's just this periodic mode that allows them to progress through their environment. And I think one of the issues that we will deal with a little bit with this talk is just what is the environment that legged locomotion is going through. Why gaits in legged locomotion? Because we're bilaterally symmetrical. Most organisms are, and so there are certain footfall patterns that are possible given the number of legs you've got. So in terms of the distinct footfall patterns that are possible, that is determined by the number of legs with the relationship 2n minus 1 factorial. And if you remember your factorials from grade school, that's the product of all of the numbers leading up to that value. So for people, that's 2n4 minus 1 is 3. So we've got a factorial of 3, which comes out to be 6 distinct possible gaits that are repeating. And these are the walk where we've got some overlap, the run where there's a flight phase in between. There's one kind of skipping where you maintain the relationship between the limbs, another one where you're changing leads each time. There's bilateral hopping, and then this weird gait is physically possible, but nobody ever uses it. And the issue is there's all these gaits are possible, but we select walking and running almost exclusively. So why is that? Now it gets a little bit more complicated for quadrupeds. That's 2n minus 1 is 7, and 7 factorial is 5,040. And my former grad student, Delisle Paulette, was working on gait models for that, and he put together this illustration where the filled diamonds are indicating that the foot is on the ground, and the open components is when the foot is off the ground. And so here are the options available for a quadruped. And yet, with all these options, they only use a small handful of gaits, certainly more than bipeds have, but it's only a few gaits that they select. And the question would be then, why are they limited to those specific gaits? And here is a brittle star. It's got 5 appendages and moves along quite well. I didn't find a video of them changing directions, but it's really cool because they just changed the legs that they happen to be using. And so with 5 appendages, now we've got 362,880 different footfall patterns possible. And then I don't know anything about spider locomotion, but if we had 8 legs, then there's 1.3 times 10 to the 12th options. And again, I would submit there's a tiny, tiny percentage of those possible gaits that an actual spider would use. So then the question is, what is limiting the use of the possible gaits? But let's stick to human bipedal locomotion. And so we can think about the differences between walking and running that might occur to us. And the first one, of course, is speed. Walking, you walk at a slower speed than you run. But I would submit that you can actually slow down and run in place. There's no dynamic difference between the running motions of running fast versus running in place, but you cannot walk in place. Marching is something different than that. As a matter of fact, even going at a slow pace, some of the stability changes, and so even very slow walking is different than normal walking, where some of the dynamics add stability just naturally. The same way as riding a bike at 0 velocity is very different than riding a bike at 30 kilometers an hour, right? You lose the self-stability. So I don't think the speed naturally distinguishes walking from running. Foot contact, we've got overlap, as we mentioned in the gait pattern there, and no overlap of feet in running. And that is characteristic of human walking and running, but it's not characteristic of other bipedal terrestrial forms like these birds that naturally run on the substrate. And so we can see here in this range where gait change occurs that in the humans, there is a substantial change, but there's a smooth gradient in birds. And so birds can be running with overlap, and they could be walking with overlap. So the overlap, non-overlap, that characterizes human walking and running, but it doesn't characterize bipedal walking and running itself. Another one is energy transduction. So in walking, the argument is that there's a potential and kinetic energy exchange during the gait cycle, whereas in running, it'll be a kinetic and an elastic recoil. And we can look at that here. If we're walking, as you fall forward, now the potential energy goes down. So we're falling forward here, potential energy going down, but kinetic energy, the velocity of the fall increases. Then hopefully you stick out your leg and you start going up again. So now potential energy so kinetic energy is converted into potential energy, and you go over the top like an inverted pendulum. Whereas in running, kinetic and potential energy are in phase because you're coming down and landing. So you're losing potential energy and you're hitting the ground, you're losing kinetic energy. But then as the leg is strained and then recoils, now we gain back that. So what we're looking at here is the strain energy in things like tendons and muscles and stuff like that. So there's this idea that the fundamental difference is this potential kinetic energy exchange difference between these two. So one definition of walking is the center of mass is at its highest point in mid stance, whereas the center of mass is at its lowest point in mid stance in running. And again, that does characterize human walking and running, but I don't think that's the issue that really tells us a lot about them. And then there's another one that is this low dimension template for neural coordination, and acting where walking is a pendulum form and running is a bouncing spring type situation. And this was put forward by Bob Full and Dan Kodacek. The idea was that because there are so many degrees of freedom with all the joints and muscles, that it's very difficult to imagine the brain being able to manage all this stuff without some kind of a simplified lower dimension template that then helps to coordinate the complex system, and they're nipping off little pieces so that they can come up with a strategy for movement that doesn't overwhelm the central nervous system. And that's yet to be determined. But here's a similarity that really struck me as insightful when I was introduced to it. So in running, we've got a contact phase and a non-contact or flight phase. And in this, we take off, which means we have to go through the air. Gravity's acting on us all the time. So we go up and we come down. So we change from going up to going down in the middle of the flight phase. And that change from going up to going down is completely passive because it's directed by gravity. We don't have to contribute anything to it. As a matter of fact, there's nothing we can do about it, okay? And then when the foot is on the ground, now there's another change in vertical direction, and that's from going down to going up. And that, just like this spring system here, is completely mediated by the legs. The legs are the thing that cause the change from going down to going up. That's what they're doing. And in walking, we've got in single stance and double stance. In single stance, we change from going up to going down. So here, as in single stance, we would be at the highest point at mid stance, but then we start falling forward. Well, that again is mediated by gravity and really doesn't take much in the way of control on our part. And then during double stance, that's when the center of mass is at its lowest point, and that's when the legs again mediate the change from going down to going up. And that's where all of the work is done in walking, and that's why it costs, largely why it costs energy to walk at all, okay? Because you're changing direction. And in both gaits, we've got a passive change from going up to going down and an active change of going down to going back up again. So if we look at the ground reaction force, should be familiar to everybody. We've got this characteristic double hump vertical ground reaction force, and then a deceleration and an acceleration back again as we put down our leg and sort of vault over our stiffened leg. And this type of record is excellent. Well, there's all kinds of little nuances here too. So we can see things like this little positive bump when the foot hits the ground. That means that the foot is being retracted at the time of contact. And that is an important feature for stability in the system, and that's been shown. So these records contain a lot of very useful information. But this characteristic curve that everybody looks at is really good if you want to do something like inverse dynamics within the leg. So if you're looking at knee joint or ankle joint stuff, that's the information you need. However, that's basically irrelevant for looking at what's happening to the whole individual. And the whole individual is responding to the combined forces of legs when there's two legs on the ground. So we can sum those in the vertical, and they actually subtract in the horizontal direction. And so if we're looking at what's happening to the whole individual, we should be looking at curves that look like this, because this is what the mass of the individual is responding to. So what have we got? During double stance, we have a vertical force peak that is relatively substantial. In between, during single stance, we've got a vertical force that's less than body weight. And then we've got, before the foot hits the ground, we've got an acceleration, we've got a bit of canceling while the double stance, and then deceleration and then acceleration again in the anterior posterior direction. This happens, this peak here happens when overlap is occurring, when you're changing from the stance of one leg to the other. That's when that going down to going up transition occurs. And that's when the majority of the work in the cycle is happening. And it's interesting that it's a combined toe and heel action, that we always look at the foot and say, okay, here's the foot, here's the function of the foot. But really the foot's function is to work with the other end of the other foot to coordinate that transition. And so if we look at the human foot here, we've got an extensive heel, we've got the forefoot is long, and in this kind of heat map, it's showing where the majority of loads are. It's in the heel when the other toe portion is on the ground, and in the toe when the other heel is on the ground. So really, to understand foot function in walking, you have to think about it in terms of a coordinated one half of one foot and the other half of the other foot. And so if we look at this walking now, we can see during the transition, it's happening with one leg and then the other in that overlap. And so we should be looking at one part of one foot and the other part of the other foot to really understand what's happening during that transition from down to up of the mass of the individual. So running is a little bit different. Here we've got a recent publication from the group here at the HPL, and I'm just going to focus on this part, which is the level running, and they're just trying to model what really happens, and they did a pretty good job of it. But the idea is, in running, we've got a non-contact portion, and we've got the contact portion, and so we've got vertical force peaks that are above body weight, in between areas that are below body weight, and that's when the down to up transition occurs, just like it does in walking, okay? And the other thing about running is we're looking here at various different speeds, just from a paper I found that looked kind of interesting. We'll notice that the vertical force is substantial relative to the horizontal. And the point I'm trying to make here is, even though we think about running as translating across the surface at a speed, a lot is happening in the vertical direction in running, as far as forces go. Okay, so let's try and pick this apart a little bit. What's happening in that step-to-step transition? Well, we've got a center of mass that is falling forward. So here's the velocity vector of the center of mass as it's falling forward. You stick out your leg like a strut and then change the direction of that center of mass as it moves. And a discontinuity in the velocity of a mass is referred to as a collision in dynamics. And so unfortunately, in biology, it's a little bit harder to analyze because we have kind of squishy collisions, but the velocity is being changed and so a discontinuity, and so collision dynamics start to come in. And so we usually think about collisions as something like this, which is rather violent. You got to see it twice, but people don't like to see it more than twice. So the idea is that we think about that as a collision. What's happening? Why do we call it a collision? Because there's a serious discontinuity in that fellow's velocity of his mass, right? And certainly sucked energy out of him, maybe for days or weeks afterwards. And you'll notice it was the old vaulting horse that was on, and that might have been one of the reasons they changed the design of it. But the idea is every time we put our foot on the ground, we're changing the direction of our mass, and therefore some sort of collision is occurring, and that extracts energy. And let's look at that. So we think about, in physics class, you learned about the one-dimensional plastic collisions where you maintain momentum, etc. In two-dimensional plastic collisions, there's another thing to think about. If the collision is not direct between two objects, then there's a component that is not involved in the collision. And the idea is that then leaves an opportunity to organize the system so that you leave as much of it out of the collision as possible. And that's going to be part of the theme of what's going on with walking. Here's one that I hope you can relate to. So I'm looking, some of my students complain about my drawings that they're confusing, but this is just a simple concept. We've got a big wheel and a little wheel, and they're going to hit this obstacle here, and they both come with the same velocity. And the thing is, they hit the obstacle, which means they collide with the rest of the world, okay? But not directly, so it's not falling straight down, it's trying to roll over it. So it's got this velocity, hits this obstacle. Some of that goes into an interaction with the mass of the rest of the world. And for a little wheel, that's this orientation between the obstacle and the center of mass. And for a big wheel, it's this orientation for the center of mass and the obstacle. And what does that mean? That if we take this velocity vector and take this component out, we're only left with this. If we take this component out, we're left with this. And so how can people relate to that? If you're on inline skates on the pathway and you come to a little bit of roughened asphalt, it'll suck the energy out of your skate. Your wheels haven't changed, your bearings haven't changed. What you're doing is a bunch of micro collisions with that roughened surface. But if you rode over that same roughened asphalt with your bike, you might not even notice that there's a roughness. And so the point here is the geometry of the collision really determines how much energy is going to be left versus involved in the collision and therefore lost. So let's simplify the models and start working up from there. I've reduced the elegant human limb system to a rod spoke-like strut, center of mass. I've exaggerated this velocity vector before contact. And then what happens is the center of mass is falling forward. You stick out this rod-like strut. The velocity it hits. Now, the strut has this orientation. We would then lose velocity and therefore energy parallel to that strut. So we're looking at that velocity vector being affected by the collision of that strut with the substrate. And that means that the velocity vector after the contact is going to be smaller than it was at the beginning of the contact. And then if we were going to carry on walking in this way, which is referred to as a compass gate, we'd have to have something like a jetpack or some kind of miracle to add more velocity back into the system, okay? And so at this point, it has the same velocity, but a different orientation than it had at this point. Now, if we were to do this most cost effectively, we would not change the magnitude of the velocity vector, and we would just change its orientation. So the cheapest way you can get away with that change is following that line B. So the area in between the path that you did take and the path that you could have under ideal conditions, that's proportional to the amount of momentum loss, the energy loss to this collision process, okay? And we're going to call that relative cost of one. Now, we know we're not strut-like legs on banging on the ground. We've got a second leg. Okay, so we can do the same thing with this. Now we've got the center of mass falling down, and we hit with this leg. Okay, so parallel to that leg is showing the collision involvement. We've got the tip of this vector would follow this path, and then we can push off with our trailing leg using our ankle, maybe a little bit of our knee, and it would do an effective limb between the point of contact where the force vector is applied and the center of mass, which you're working on. So that parallel to there would bring us back to where we started from. Okay, and now if we look at this area here, it's 3/4 of the spoke-like strut compass gate. Okay, so we've got an advantage to using two legs in this step-to-step transition. Now is the reason why you need to consider collisions and the influence of collisions on walking. If instead of hitting with our heel first and then pushing off, if we push off first and then hit with our heel, it makes a fundamental difference to walking. So in this case, what do? You push off with this limb. So now you're going from here to here. Now the orientation of the velocity vector is completely different when this foot hits the ground. And so you don't have nearly the collision with the ground that you would have if you hadn't pushed off with the trailing leg. And then we hit with the lead leg. And now this area is what's lost to the system. And in theory, this is the way it should work. And in fact, there's a variety of ways to do it. But if we just look at muscle activities, and this was a modeling study from over 20 years ago, in which they did an optimization model, which is a solid line, but then you can see the EMG results of the ankle plantar flexors, soleus and gastrocnemius, being active. So this is offside heel strike. So this is heel strike on the other leg. We're monitoring the muscles on the leg that is pushing off. And the activity is virtually all before heel strike hits on the other leg. So you're pushing off before the other foot hits the ground. Whereas you might think you hit the ground and then push off to get up over the top in the inverted pendulum, but in fact, you're monitoring those collisions, trying to reduce them, because that's where energy is lost to the system. In contrast to that, in running, we've got things like the gastrocnemius and soleus are active virtually only during stance, when you're changing from going down to going back up. And then some of these other muscles like rectus femoris is active during swing because that's a flexor of the hip, and biceps femoris is active because it's an extensor of the hip. And these are actions that you're doing during swing in running. Okay, so fundamentally different step-to-step transition, even though both have a step-to-step transition, and partly that's because of the overlap that's possible. Now, this movie, of course, is one of the original ones from Landing on the Moon, and you'll notice these guys appear to be in a hurry to get someplace because they're running. Okay, they played golf on the moon, but I don't think they were worried about missing their tea time. So why the heck are they running on the moon? I mean, they spent a lot of money to get them up there, and you'd think that they'd want to wander around and enjoy themselves for a while instead of running. So the question is, why are these guys running on the moon? And I was intrigued by this question back when Claire Farley and Tom McMahon did it in 1992, because I was a postdoc in the lab where they did this work. And what Claire showed was that she had a gravity harness, and so she could reduce gravity down to 25% for the center of mass effect. It wasn't on the arms and the legs, but it turns out that that's not all that important. And then if we look at the cost of transport, which is the energy per kilogram per meter traveled, okay, then she has them running at 3 meters a second and walking at 1 meter a second. So this would be typical speeds that individuals would choose to naturally to walk and run. And what she found was that running, as you would expect, the cost of transport in running decreases with gravity, okay? But what was surprising is the cost of walking doesn't go down much for walking in reduced gravity. And in fact, what she found is that at 50% gravity, it costs the same to walk or to run. And below that, it actually costs less to run than to walk. And then the moon's gravity is about 17%. So down here, so those astronauts perceived the fact that it was cheaper for them to run than to walk. And I think we've all experienced this. If you go to the beach and you walk in on a shallow sloping beach, when you get up to about chest deep, you're starting to get down below that 50% buoyancy. Everybody changes to a run. And you think it's because the water's holding you back, but it's holding you back whether you're walking or running. You somehow naturally realize in this weird circumstance that running is a better way to move than walking does. And I'd like to understand that control thing at some point. But now we're looking at this phenomenon. Why does it occur at all? So one approach we took to it was to do an optimization model and put into it just the things that we thought were important, and then see what the model comes up with. And so this model, simple as it is, it requires substantial calculations to make it work. The model determines how to move in order to minimize total work. And so we don't constrain it to particular step lengths or anything like that. We provide a speed that it needs to go at and define walking and running according to whether there's a flight phase or not. But then everything else is left up to the model to optimize relative to the total work that it has to expend with its actuators, okay? And then we wanted to also compare that to what people actually do. So we developed our own gravity harness, and we did this differently than anybody else had done because we use a metal spring when most people use a lossy elastic spring, so that the idea is so that as the spring stretches and contracts, the forces don't change, which is what you want. What we did was put in a lever that compensated for the change in force as the spring stretches and contracts. And so then we would measure exactly what the upward force was and how constant it was on the individual. And so just to have a look at what this looked like in the lab. So here's somebody running at a reduced gravity on the treadmill in one of our experiments. And I love this video because it shows that the individual really does feel like they're in reduced gravity. I don't know what she thinks it was doing to her arms, but this was her natural reaction to being in that environment. I'd always let people play in it for a while, but you can see our lever system and the spring in the background there. Okay, so what did we find? Nothing new. This is our data compared to Claire Farley's data for the walking and running. What we did was normal gravity and 50% gravity, but what we did was multiple speeds at each of those. And that way we could do this kind of a plot where we could compare the empirical results to the model's results. Okay, and this is again cost of transport versus speed for two different gravity conditions, 1G and 50% G. Okay, and what this is showing, and the same model, and it really is matching the empirical pretty well. Walking is highly sensitive to speed. It's got a steep slope in both the model and the empirical, but it's insensitive to gravity level. These curves are laid basically over top of each other, and that gravity has very little effect on walking. Whereas running is insensitive to speed, and people often wonder about this, but this is cost of transport. It's not power. So the power you put into running faster is real, but you're going more distance. So if you account for the distance you've traveled, the overall cost is basically the same. And we've known this since the 1930s as well. But running is insensitive to speed, so it's flat regardless of what gravity you're at, but it's highly sensitive to gravity. So what Claire and Tom found, we shouldn't have been surprised by, because we already knew that running was insensitive to speed and walking was sensitive to speed. we knew there was differences there already, and gravity is just another one indication of those differences. So the nice thing about doing a model is that then we can take it apart and ask, why is that the optimization? Why does it arrive at that optimization? And here's our explanation. In walking, the cost is dominated by an oblique collision loss, the interaction between the center of mass velocity and the ground reaction force vector. And the interaction of those determines what kind of a collision is happening. And it's dependent on the velocity and step length. Why would it be that? Velocity determines the magnitude of this vector. Step length determines the angle of this vector. And the faster you go and the longer the steps you take, the worse the collisions are. And therefore, how do you get to go faster? You take longer steps and things like this. You don't take little steps. You take nice long steps as fast as you can. And so the collisions mount up and the cost increases. This is an interaction between your velocity and your foot on the substrate. So gravity really doesn't have much to do with it. Okay. And it results in speed increases cost directly. So that makes a great deal of sense if you're thinking in terms of collision interactions with the substrate. In running, the vertical velocity dominates the collision loss. So it's near constant per step. And that is, you go up so that you've got time to swing your leg to get it in place. But if we look at this, you try and get your leg as directly underneath your body as possible. And that's why vertical forces dominate in running. And no matter what gravity you're at, your landing velocity is the same as your takeoff velocity, right? Gravity doesn't change that. What it changes is how long you're up in the air. For any given takeoff velocity, you're in non-contact for longer. So reduced gravity allows a longer stride for the same vertical velocity. For the same collision loss in vertical, then gravity has a direct effect on that because it's basically your hang time. And so reducing gravity should decrease the cost of running directly. So verified that what Claire found, and now we're explaining why it should be that way. Notice that it didn't matter about what muscles were being used or anything like that, because in the model, the actuators were the actuators. The system for walking isn't fundamentally different than running. It's just a different strategy. Strategy is available because you've got overlap between the legs. Therefore, you can use that preemptive push-off to decrease costs. And that's not available in running. And so running benefits a great deal from a reduction in gravity because its interaction is so vertically oriented. Why does walking cost decrease slightly? So we are seeing this. That doesn't fit with our model of the interactions with the collisions, et cetera, which should be pretty much independent of gravity. So we also looked at step length. And a little bit busy here, but in both, so in running, step length increases, and that's why the cost goes down. It's subtle here, so I've exaggerated it in this place, so we're just changing the size of the axis. Here's 3 walking speeds and step length for a number of subjects. It increases as gravity goes down. You take longer steps. Why would that be? Note that we're keeping people on the treadmill, so it's a constant speed at these 3 different speeds. The model predicts the same thing. Reduced gravity, forward speed doesn't slow during stance. So you slow going over in that vault to mid stance because you're exchanging potential energy or kinetic energy for potential energy. But in reduced gravity, you don't have much potential energy, so you don't slow down. So going over the top is faster than in gravity, doesn't slow down. And so to go the same speed, you don't have to go as fast at contact. Therefore, your collision would be less. But instead of taking less collisions, we accept the collision, but take a longer step, which means we travel farther for the same collision loss. And therefore, the cost of transport goes down a little bit. So we can explain all of these subtleties involved with the influence of speed and gravity. So take-home messages. In locomotion, the legs manage the interaction between the individual and the environment. So what the heck is the environment? The environment is gravity and substrate. And it's acting as this interaction with the legs mediating that interaction between the mass of the individual and the substrate they're moving on. The basic role of the legs is to manage the trajectory of the mass of the individual. And usually we start thinking about, okay, what do normal legs do, what do pathological legs do, etc. But I'm getting convinced that what we need to do is follow what's happening to the center of mass so that we can figure out how it should be moving and then start interpreting how the legs are or are not providing that control or management of that trajectory. Walking has double stance that allows for that preemptive push-off that is really important in reducing the overall collision cost with each step. And that's critical to effective walking. And if you can't do that, you can't walk effectively. And so what kind of circumstances would change that? There's lots of pathologies, but lots of pathological footwear. So like high-heeled shoes don't allow that plantar flexion of the foot at the critical time. So then you've got to use other joints to do the same thing. So ultimately, high-heeled shoes make your butt wiggle. That's the only joint you've got available to compensate. Walking is a compromise between a stiff leg, low work, but large collision. So if we walked like that compass gait, our legs would be stiff and therefore our muscles wouldn't do any work. But we'd lose a lot of energy to the collisions, just like we saw. We could also get rid of the collisions by walking with completely bent legs so that we didn't rise or fall over the gait cycle. But that would take a tremendous amount of leg work. So what we do is a compromise with relatively stiff legs with a little bit of movement and managing the accelerations at the proper time to get away with using as little energy as possible, even though we've got to do some. And running has only single contact, so can't use that preemptive strategy, which means it has dominant vertical collision, and that changes its relationship to speed and gravity. So I like this. I like teaching or talking about locomotion in the YouTube age because you get all these cool videos to play. I hope they're coming across on the Zoom reasonably smoothly. But look at what this guy does. Now, if I argue that the legs are to manage this animal's center of mass trajectory, you get that from this. And I submit that if this animal lived in some kind of warped gravity environment, that might be the only gait that it uses, because at that particular instant, all it has to do to manage its center of mass interaction with the substrate is that little two-legged flip in the going over the top. Here's another one. This is the quadrupedal speed record in humans. And I think you can see that but-a-dump that comes into the William Tell overture, emulating a horse gallop. This guy actually took it from a certain kind of monkey that runs like a greyhound, but he did beat the speed record. But I submit that this is the gait that he had to use in order to do that, because that's the gait that manages the center of mass trajectory under those circumstances. And so then I'll finish with the actual horse gallop, where we ride off into the sunset or whatever and say thank you, and I'm happy to take questions.
Great. So, John, maybe you could stop sharing your screen. Great. For those of you on Zoom, I kindly ask you to turn on your Zoom camera if you're comfortable,
Let's see.
to allow for a better discussion. For those in the room, you can raise your hand if you have a question. For those of you on Zoom, please feel free to use the raise hand function under reactions.
So you've got the Zoom, right? I don't have the
it's still
Zoom.
running.
Okay.
Art, please go ahead.
John, I enjoyed seeing the reminder of just how many gait combinations are possible for, say, quadrupeds. And one thing I didn't realize is that there were so many. So I'm doubtful that Delisle actually tested all of them. So my question is, just how many different gait patterns did Delisle test, or what fraction of what's possible? And then what are the chances that somewhere out there there's a quadrupedal gait that's better than what we know about?
So with that many options, I suspect that there might be the evaluation of the possibilities is truncated, but in the development of quadrupedal locomotion prehistorically, I would think there's everything from the mud skippers flipping around to the elegant modern animals that we've got, and maybe some of the dinosaurs were even more elegant. Delisle focused mostly on walking and trotting, and galloping is a complex gait because it's asymmetrical, and so he did not in any way test all of those possibilities. But in walking and trotting, he found that his model optimized to specific gaits depending on some unexpected characteristics of the animal, such as the longitudinal momentum of its body in terms of its ability to turn or flex up and down.
So if you try a different gait in the model that's not one of these, are basically all the other possibilities, do they all turn out to be far worse, or are there any that are sort of close to walking or trotting?
So that's one of the interesting aspects of looking at galloping. There is a model solution that some horses use that always comes out as superior to the asymmetric gallop that horses and most animals like dogs and stuff use anyway. And that's what the Icelandic people call a tolt, where it's a running walk, basically the pattern of a walk, but at running speeds. And the center of mass doesn't go up and down very much. And that's why the people who ride horses like it so much, because it's a very smooth gait. And so what we're thinking then is that there's something missing from these simple models that we use that would allow that to be the optimization when in natural circumstances that doesn't turn out to be the solution.
And I guess the tolt is special because that's the only kind of horse that is able to do it, right?
There's a couple of different breeds of horse that do it naturally.
How about dogs? Can you train a dog to do a tolt?
I don't know. I would imagine. So there's some odd gaits. You remember Manoj Srinivasan and Andy Ruina came up with an odd bipedal gait in one of their models, and we found out that people could be trained to do that gait, but people never use it. It sort of falls in between a walk and a run. It's a very odd thing. As some people have good facility at it, some people don't. I think people who can dance and things like that probably are better at it than the rest of us. But you can discover these odd gaits with the simple models that can be emulated biologically, but then there's some reason that they don't fall out naturally. And those are the sort of things that we look for. That when I said in the model, we put in everything we thought was important to determine the dynamics of walking and running, we obviously didn't put it in for the quadrupedal model everything that was absolutely needed.
Great. Thanks.
I'll read a question out loud from the chat. This is from Ethos. Everything else being constant, is there an advantage to adding more limbs? Is there ever a benefit to crawling?
So galloping is a completely different story, and it's another one that I very much enjoy. But what's happening in galloping is you're using the forelegs instead of alternately like you would in a walk or a trot. You're using them in series. And it's, you know, if you're thinking about that interaction from going down to going up as the legs being spokes in a wheel, the more spokes you have, the less you have to go up and down. And so in order to go fast where collisions would be really bad, horses and dogs and things change their gait to this canter and gallop, where they spread their legs out so that they can use them as spokes in series rather than spokes at the same time. And so I would think it is possible to increase the number of legs to decrease the collisions. However, now you've got more legs to manage, and that might have some negative effects.
Great. Reed, go ahead.
Hey, John, I really enjoyed that. So a few years ago, we published a paper on different algorithms for determining heel strike and toe off. But what we did was we queried the database, and because we'd heard a talk on grounded runners. So there's a percentage of runners, and based on our query of a few thousand people, about 10 to 12% of people run in a grounded manner, meaning both feet are on the ground.
With overlap. Yeah.
With overlap. So what we found through this algorithm, so we had separate algorithms for running and walking, obviously, but neither one of those algorithms work for grounded runners. Now, at the end of the day, the editors didn't want us to include that data. We turned it into a short report. But it's always fascinated me that there's this population of grounded runners, and they are running within 1 standard deviation of the rest of the population of, I guess, typical runners. And we also have walking data on them as well. So they all prefer this gait style at a running speed, if you will. So they're not running slower than anyone else. They're maybe on the slower end, but where do you think they would fit in your spectrum of like half a G to a full G? Do you think they're going to be an even split, or more resemble runners or walkers? What do you think?
So if you don't define running based on footfall pattern, if you define it based on the dynamics, then even their grounded running will be more vertically oriented. So they would follow natural runners in terms of sensitivity to gravity. The reason I think you've got grounded runners is that their leg compliance is higher than normal runners. And so they've just got less stiff legs, or they move in a manner that's less stiff. The reason I say that is because of a evolutionary anomaly that put the acetabulum of birds at the back of their sacrum, and they have bodies that are horizontal. They actually use their femur to get their leg under the center of mass, which naturally makes their leg more compliant, and that's why they have that smooth transition from walking to running and a lot of grounded running.
You think a grounded runner is explained anatomically?
So I would bet that their limb is more compliant than other runners of their same size and stature.
Well, I'll agree with you on the stiffness component, but you were explaining like acetabular position might explain it.
No, that's the birds.
Okay.
The birds are derived from dinosaurs that had a big tail, but a big tail doesn't fly very well. So they got rid of their tail, which meant they got rid of muscles that help to keep them upright. And so they've got to change the strategy, and that forces them into a more compliant limb. If you watch a video of an ostrich running, its knee sits here underneath its body and hardly moves, and the rest of the leg from the knee down is what flails back and forth.
Okay. Do you think a grounded runner has an advantage over a typical runner? And by the way, grounded runners exhibit all types of foot strikes. They're forefoot strikers, mostly midfoot strikers, but also rear foot strikers as well.
Yeah. So there's going to be advantages and disadvantages. I would think that the magnitude of the forces applied to joints would be let's say the amount of increase in joint force would be less because they're more compliant, therefore not hitting the ground as jerky, but they're doing more muscle work because their leg is compliant. So it depends on what you're looking for.
Yeah, their knee is always flexed. They don't really exhibit like an extended knee at Footfall either. Okay, great. Thanks, John.
Rob, do you want to go ahead?
Oh, right. John, you talked about running and that you had the video showing footfall sort of under the body. And so it's not quite the same as your wheel hitting the stone. You're not getting that stopping effect. But in kangaroos, the faster they go, the further they put their foot out in front of them. So even though they're bent over, their toenail will hit the ground well out in front of their body till well behind. Now, they won't, I describe hopping in a kangaroo as being the same as just one leg running. It's just duplicate, so it's just one running. But you also mentioned, and I'm not sure that I followed it, a more compliant system in some runners, because in kangaroos it's a very compliant system. They, in my view, extend the length of their leg by folding out the joint angles of knee, hip, and ankle to get it out further. But then they've got a very compliant, much longer limb that goes under and pushes back. In a way, is that the opposite as how you describe human running, where they put the foot directly down?
Yeah, so just in case that didn't come across to the Zoom audience, Rob is asking about kangaroos, which have the very fast bipedal hop, and he's suggesting that as they hop faster, their stride is actually longer, and it's not just the time in the air, it's actually longer on the ground, so the limb has to extend farther out in front. There's going to be a collision, but he's saying that the limb is relatively compliant and that they don't vault over it like human runners might under those circumstances. I think it's very similar to human runners, but they've got specialized adaptations in tendons and I suspect muscle that hasn't been recognized that can allow that maybe storage and return of kinetic energy. One of the things that if somebody looked very closely at the models that I was showing of walking and running versus the empirical, the actual predicted cost of running was quite a bit higher in the model than in the human, but we didn't have any elasticity in the model. And we know there's going to be some influence of elasticity. So that idea of the pogo stick or spring is there. It exists, but it's not a determinant of the running gait. If we didn't have springs, we would still run under those circumstances of speed or gravity or whatever. And for a long time, it was thought that running needed springs, but that gives an evolutionary conundrum, because how do you develop a gait that needs springs if you don't start off with springs? And why would you develop springs if you didn't have a gait that needed them, right? But yeah, I think the kangaroos are an interesting anachronism, but I don't know much about their ground reaction forces and how they respond to speed and things like that, but I think it'd be very interesting. A fair amount been done on their physiology in that regard, but not a lot has been done on the physiology of their muscles and mechanics of their gaits.
And equally, I think there's more that needs to be done with kangaroos running in the field, because I think that on the treadmill, I just don't think you're seeing the same gait, nor are you seeing the higher speeds.
Mm-hmm. Yeah.
We can do that.
Looking forward to it.
Benno, go ahead.
Yeah, thank you. It was a very nice lecture. It's nice to, in between, to go back to the basic understanding of locomotion. I have a simple question. You mentioned at the beginning that walking and running are effective, cost effective. And I always thought they are not. Am I wrong?
Okay, so if you are saying flying and swimming are more cost-effective ways of moving, you're correct. But they're cost-effective ways of moving on two legs.
So you would say they are cost effective for everybody or every animal that runs or walks on two legs. Is that what
So
you said?
if they're going to use legs for locomotion, those two gaits, except for weird adaptations like kangaroos and things like that, that's a solution which is energetically cost effective.
Okay,
And when I put it in my title, I wasn't being nearly so specific. I was just pointing out that they're effective because that's what we use, and we don't train athletes to do some other kind of movement in running. So there aren't, I don't know what kind. That's one of the things that's unfair in Olympics, and why swimmers win so many medals when runners don't have as many, because they don't say hop, skip, and jump 100 meters versus another gait at like breaststroke and butterfly and stuff like that. These made up gaits that you can do in the water, you really don't do that much in terrestrial locomotion.
okay, thank you.
Brent, go ahead.
Thanks, John. One thing that I think you've dabbled in, but I don't think really talked about today, was sort of the walk to run gait transition. And my question is, it doesn't seem that people switch from a walk to a running gait to be they don't do this at a gait where it's sort of efficient to do so. It seems like they switch to a running gait at a speed where it's still much more expensive from a cost of transport perspective to start running. Do you have any explanation for why humans, or I don't know what other bipeds do, but why you would choose to switch to a running gait if it's not the most economical thing to do at that specific speed?
Yeah, so if I could just reinterpret your question for the audience. So as you speed up in walking, we saw walking is highly sensitive to increases in speed, whereas running cost of transport is flat. So those two curves intersect at a speed. And so it's the same metabolic cost of transport, walking and running. And I use that in one of my studies to try and figure out how much it costs to change gait, because if walking and running cost the same at that speed, then you have people change gait like every 10 steps, every 15 steps, every 6 steps, every 2 steps. Then you can work out what the cost of changing gait is, which is not a trivial thing to work out. We weren't all that interested in it. We just were trying to show off we were clever enough to figure it out. People have since used it for things like analyzing how soccer players should move on the pitch and stuff like that, because the transition certainly does cost substantially. But when we were doing those studies, I noticed one thing, that speed running is absolutely trivial. It's a slow jog. It's just, well, for somebody my size, it's just over 2 meters a second. But I would never walk at that speed. I would never walk at that speed, even though the cost is identical. And so my theory, which I now have a student working on, is that because of that critical push-off time in walking, you've got only a couple of muscles that are determining that metabolic cost for the whole individual. Whereas in running, you've got a bunch of muscles that are spreading out that cost. And so per muscle, not per individual, it's much more cost effective to change to a run than it is to stay at the walk at that speed as you approach that crossover point.
So would you say that it's a local trigger that's making people switch from a walk to a run? It's a few highly strained muscles, highly stressed muscles that are doing a lot of work. So that's kind of what's forcing you to transition.
Yeah, that those muscles are coming, that are approaching their limit, and there's an alternative that relieves them of that costs more globally, but doesn't cost the muscles as much.
In that instance, do you think it's pain that's driving the transition, or uncomfort?
So I think that whole thing, the discussion is a little bit artificial because we put people on a treadmill and constrain their speed. And we ask them, okay, when are you going to transition? So when they transition, they're stuck at that speed. In natural circumstances, you would change your speed and use that extra energy to go faster because it doesn't cost you any more to go faster.
Yeah, but I do think that there's different protocols, and I do think people have used sort of, instead of stepped protocols to identify the transition speed, people have used graded approaches where, or ramped sort of protocols where they just start increasing speed and they do it over and over again. And people always, I don't think there's a lot of variation in the stepped protocols where you have people walking for a long time. Oh, do you like that?
What I'm saying is, when they transition, you need to allow them to go faster because for that same cost, they could go faster. And that's what they would naturally do. So you need to have a protocol that went step, step, step until they transition and then have it self-paced, a feedback treadmill.
But not pain or uncomfort.
So it wasn't overt pain, but it certainly did seem like discomfort walking at that transition speed for us.
Yeah.
And we also noticed we overheated.
There's a Wikipedia page for walk to run transitions, and it talks about all the potential triggers. You should go on the Wikipedia
Well,
page.
we want to determine the trigger first before we get involved in that discussion.
Yeah. Thanks.
Hey, Brent, did you start that Wikipedia page? Because you did some gate transition stuff with Alan Hurljack.
I don't know why I just raised my hand again. No, I did not, but I suspect it is a Hurljack love supporter because they do talk about his theories. Yeah.
Well,
I'm gonna make sure that you're added to that page then.
He was looking at the ankle dynamics. He was looking at the kinematics of the limb, and his proposal was that a certain acceleration of that ankle was what caused the transition. What I'm saying is it's the muscles that are attached to that ankle acceleration that are causing the transition.
He's done all those studies. He's got a paper looking at kinematics. He's got a paper looking at kinetics. He's got an EMG paper as well. Yeah. So he's done, I don't know, 5 or 6 studies. He's also done it looking at joint moments and whatever. And all those studies tend to suggest that it's this fatiguing of or uncomfortableness or whatever of the ankle dorsiflexors. Yeah.
It's tibialis anterior. He's got 9 papers, by the way, on this, but it's tibialis anterior is the main driver. Because as soon as you get to that top walking speed, tibialis anterior is about 300% higher than when you switch to the transition and start running. But I agree with you,
so
John. I think
it's exactly true.
Where you speed them up. I agree.
At that speed, we used to refer to it as a foot slapper because when you're hitting with your lead leg, tibialis anterior is the only one that stops your foot from slapping on the ground. So tibialis anterior, as well as the plantar flexors, could be the key.
John, for years, I've heard the conversation about higher energy cost of transport, and I've always thought, what's my sensor for energy cost of transport, and do I really care about it? And with kangaroos, they say, that they can travel at a higher speed without having as high cost of transport. We could argue that. But you said something before, earlier in the talk, about sense of effort. And I think that reflects exactly the same thing. I don't see kangaroos out there going, well, if I'm going to travel this far, I'm going to go to a higher speed. But I certainly see lazy kangaroos. My backyard's full of them, so I see lots of kangaroos. And I certainly see lazy kangaroos who just don't want to do something. When you transition from walk to run, and when you reduce gravity, are you aware, I haven't been on your machine, but are you aware consciously of the sense of effort? And while you write it down as the energy cost, is it totally reflected in a sense of effort where you could give it a org scale of 1 to 10 in sense of effort? And has that been done?
So I like the quantification of the metabolics, and that's carried me a long way, but I know that's not the complete answer. It's just one part of the answer, and it's one that I've been successful with. When you're in the gravity harness, you feel very athletic. And when I was in Florida, I had a hypergravity harness as well. I could pull down on people, and that made you feel old. I mean, it was bad news. So the thing is, you have a sense of being relieved in this. And just like the fellows on the moon, your body basically takes over and tells you what you should be doing. And that kind of insight, I remember Max Donnellan did a study where he had he had a treadmill that was controlled by the relationship between the speed and the frequency of your steps with foot switches inside your shoes. And we've got a relationship between frequency and speed that we naturally do in walking, right? So because he had his diabolical computer in between the foot switches and the speed controller, he could change that algorithm. And so he could set it up so that your body would feed back to itself to constantly speed up, to slow down, or to go back and forth between speeding up and slowing down based on where you were in the cost surface that he put you. So you somehow could, so every step we take, whether it's natural or not, it costs us a certain amount, and that makes a bowl-shaped surface. And if you put somebody on a certain part of that surface, it'll have a certain slope, etc., and you'll try and get back to what you think is natural. But if the system doesn't respond in a natural way, it'll take you for a little ride. And that was interesting to me because I knew what was going on when I was on it, but I felt like my body was taking me for a ride. I wasn't necessarily making the decisions, and it was very hard to override it, even if I understood what was going on. And I think more of that is going on in our natural locomotion than we imagine. And I would point to what that dog was doing going over the top. It's not thinking about, oh, I need to do this maneuver. It's thinking, I need to manage the center of mass trajectory, and I'll do what's most cost effective under these circumstances to do it. So I once wrote a paper that argued and showed some pretty good evidence that rather than being stereotypical gait walking, it's remarkably plastic, and you'll do whatever is appropriate under the circumstances that you're in. And so when we think about the neural control of things like that, one of the reasons we all look the same walking is that we're all solving the same problem. And there's one solution to it, apparently. And so we all do basically the same thing. If we were in a different circumstance, we would do something completely different.
But the speed to walk, Jim and I both walked at very high speed, and that could be an inherited psychological problem, or it could be, would you be able to predict from that what our type of gait would be? Because I can walk to the lab, and I've had students had to jog beside me to keep up, and that's just my natural gait. So would you, with saying that you have this bowl that I've seen descriptions of, would you be able to use the model and predict some part of my gait?
So even in the meticulous studies that I did, I had outliers, people who did relatively unusual things. Generally, the trend was the same, but they might be displaced from everybody else's curve for whatever reason. But one of the things we need to keep in mind about optima or minima in biology, I had a colleague who was a very clever individual. He was the individual that flew a toy airplane from Newfoundland to Ireland. He actually, but just to prove that he could do it. And he was successful. But he aeronautic engineer, of course. His name was Tad McGeer. He pointed out that optima and the same thing for minima are flat and fuzzy. So there is a point that is optimal for us to metabolically to walk at, but to vary off of that to some degree doesn't cost very much more, because that bowl is pretty flat on the bottom. And so who knows what kind of psychological, physiological, morphological differences might come in to somebody's personal choice of walking speed. There have been studies that show different cultures generally walk at slightly different speeds naturally, and especially urban environments, people walk faster, etc.
I have a question about your cost of transport versus percent gravity results, and the walk and run lines cross right at about 50% gravity. Is that coincidence, or is there some dynamics?
So I'm comparing my data to Claire's data, which I thought was pretty good, but it was done a long time ago, and I am familiar with the equipment, and Dick Taylor, who was running the lab at that time, was renowned for investing in people and not equipment. So the equipment was old and funky. Her results are really pretty good, but they do differ. So if I recreated those with my harness, the crossover point would be a little bit lower gravity than she found. So I don't know. It's around there someplace. But I don't think, yeah, I mean, 50% means something to us, but it doesn't mean that to gravity, because 0 means you go up and you don't come down, right? So it's completely different down. We got down to about 15% gravity, but many people were unable to even walk or run at that speed, at that gravity level.
Walter, go ahead.
Yeah, thanks, John. That was very inspiring, and you know, makes you think. And I had a couple of very simple questions at the beginning, but I think the first one you answered already, because I was curious how you came up with the 2n-1 functional type of a equation for predicting the number of gates, because I could instantaneously think of many more gates, and I could see that I could skip on one leg only, or, you know, as you mentioned, a triple jump already, where people go right, left. Or in track and field, we have the hurdling exercise where people go left, right, left, right. But I guess you call these, what do you call them, non-trivial gates or artificial gates, and they do not count?
So yeah, I guess you could develop a variety of different things, but this is in terms of the footfall patterns that are possible. And so
so why does skipping on one leg for a two-footed person not count, or why does
yeah, so I guess the definition is using the legs that you've got.
Using the leg they got, okay. And the left, right, or would not work because that's not a natural.
So
like, what's a trivial footfall pattern? What's a non-trivial?
That's just a variant of the skipping gait, right? Yeah.
Okay, good. The other question that I had is, if I understood you correctly, you said you cannot walk at 0 speed.
That's right.
I missed that. Why cannot?
Okay, so if you're running, you're running, and you know the motion that has the vertical bouncing and everything like that. You can slow down until you're making no progress, and you're still doing the same gait. But walking, if you slow down and get to 0 velocity, you're not really walking. And that's because walking requires that falling forward. Oh, thanks. Appreciate that.
Okay, so there's this certain definitions about walking that you would argue then are, so when I walk at 0 speed, which I thought I can do, but then you would argue that's actually not really a walk.
You'll notice all you're doing is lifting your legs alternatively, and it's not like walking.
Okay. Yeah. Okay. And so what is race walking? Because, race walking is this thing, as you probably know, where people try to go really fast. And when they do that, they are supposed to have a double stance phase. But of course, they absolutely minimize that. They have the stance phase that's maybe a millisecond. So what would you say is race walking? Is that running or is that walking? In your dictionary?
Yeah, so it's a very artificial gait designed to circumvent some dynamic consequences of going that fast without running. And one of them is if you vaulted over your leg, your foot would come off the ground because of the centripetal force. And so they don't want that because it's not in the rules of that particular race. So they've got to compensate by tilting their pelvis to lower their center of mass so there's not nearly as much centripetal force going over the top. And then they also use their leg in a slightly different way. They flex their knee, etc., to reduce that centripetal force, to keep their stance leg on the ground at that high speed. And then, of course, they have to have at least some double stance.
So in your definition, race walking would be walking, it would not be running, according to your definition.
That would be, in my consideration, you would use that preemptive push-off that I said was so important in the step-to-step transition. You would do that almost independent of the next footfall, but you would still have that same walking transition, managing the force, the vectors, the velocity vectors of the center of mass. And then they also have to manage the velocity vector as they're going over in their stance limb, or the centripetal force will lift their foot off the ground.
Yeah. And then I was intrigued by you saying that the cost of transport, was independent of the running speed. And I would assume that is true for speeds where you stay fully in the aerobic area, because as soon as you go a bit faster than that, then you go in the glycolytic cycle. And then, of course, the glycolytic cycle is much less efficient. And I would assume the cost of transport would tremendously go up if you run like too fast, so to speak.
Yeah. So it's fairly flat over a wide range. And as I say, I think Magaria was the one who discovered that in the 30s. But here's the proof that it has to be parabolic. If you're running in place, your energy costs are high, but you've got no distance covered. And so the cost would be infinite in the cost of transport.
Yeah. And just a last comment, to what Reid was saying very early on about the grounded runners, and and I'm familiar with the grounded running, and the fact that some people at a given speed will do the grounded running and other ones will do kind of what we would call the normal running. But I think we also have to say that from a running point of view, that only really happens at slow speeds. Eliud Kipchoge,
if they were running fast enough, they couldn't do grounded running.
Yeah, exactly. So I mean, from a if you look at jogging, then it might seem like a regular speed, but really, I think from a running point of view, those are really extremely slow speeds where you do that. I mean, you couldn't win an Olympic Games by doing a grounded running type of thing. So, in fact, not even half the speed. So you really have to run at a speed that's kind of at the probably the lowest 25% or so of what people might be doing in a marathon run or so. Thanks, that's all.
Any other questions?
Yeah, there's a question in the back here.
I just have one really quick. I don't know if I missed it if you said it. I was wondering how fast the transition is, like this adaptation to different gravity conditions.
Oh.
Is it within one step? Or
Yeah, good question. So for those on the Zoom, the question was, how long does it take somebody to adapt to the different gravity conditions and assume those the appropriate gait and energetics for that gravity? Just like the moon guys, you do it automatically and virtually immediately. We haven't looked at it, but we've even done studies where we control, well, because step length and step frequency add up to be speed, right? Okay, you can control speed, put somebody on the treadmill, and then they'll do some kind of combination of speed, of frequency and step length to create that speed. And then you can change the speed, so you can control the speed and see what the individual does. They do something different if you control the step length, like having them step on different markers on the ground and then choose the speed and frequency that they want to go at. Or if you have a metronome beat and control their frequency and allow them to walk down the hall, they'll use a completely different speed frequency relationship than you would when you're on the treadmill. And people automatically do that. And as far as we could tell, it was 3 steps, something like that. And Max Donnellan has looked at some of those transitions as well. And he's looked at it more extensively. And he has concluded that there's a fast acting within seconds kind of thing. And then one that's a longer acting that may be related to bringing the metabolics to their optimum that might be 10 minutes or so.
Can I just quickly follow up on that? Because, I was intrigued by that, and when we go to the moon, and when these astronauts go to the moon, they have the physicality of a human being living in a heavy gravity environment, and so I was thinking our muscles are probably completely overbuilt to the moon, and I was imagining if we ever lived on the moon continuously and had that type of gravity, then we would need much less muscle mass and bone mass and that type of thing. And if in a million years of living on the moon, and we had, we were much weaker producing, for example, muscular-wise, would we still walk the way as humans that go up there now? Or once we had adapted to that gravity and everything would have scaled back, especially our muscular forces would have scaled back, would that still be the most efficient way to walk?
So, like I say, I don't think we would walk on the moon. We would run, even if we were adapted to it. But that's an interesting question. But if NASA ever asked me to help design the walkways on the moon, I would say put up monkey bars and we could go back to being brachiators, because you can eliminate the collisions completely if you brachiate.
So if you, let's say, you said that the moon's gravity is about 17%. So if you scaled all the muscle forces down to 17%, then we would still be running.
Well, that's a decent question. I have to admit, I haven't thought about it. My guess would be that it's walking is not effective because you're forcing those collisions on the system and therefore losing energy. Whereas running, it has a collision that is sensitive to the gravity. And so it goes down naturally with gravity. So I would think, regardless of what your muscles were, that the dynamics of the system would be the same.
Thanks.
Are we still recording?
Yes.
There's a reason to ask that. John, I've really enjoyed this talk, and you've cleared things up that for 30 years I've wondered about. So in all seriousness, I've greatly enjoyed it.
But they are somewhat surprising, right?
Yeah. But having gone from the serious and got to the end of the presentation, if has raised the issue of if we added more legs, it would be better. And I hesitate to do this, but there was when chickens are bred, tens of thousands in a plot, farmer's plot. Every now and again they get one with 4 legs. You know where this is going. And so one farmer just started breeding 4-legged chickens. And when he was asked, what do they taste like? He said, no one knows, no one's ever caught one.
So
Sorry about that.
But we do have what the morphologists call a BAW plan, an organization of the system. And when you have unusual development like that, it generally messes with the basic plan. And so almost always those things are less effective than.
Benno, go ahead.
Yeah, so why do humans run the way they do with the steps when they run as fast as possible, and kangaroos run by galloping or by hopping?
Yeah, so I have to admit, I don't understand kangaroos, but as Rob says, they seem to be running like people with one leg, or instead, like just like our models of running, they have basically one leg, and we call one contact the left leg and one contact the right leg. And so our models can basically run that same way as well. People are alternating legs because that's an effective way to get your leg back to where it was, to stand on one while the other one's swinging. Kangaroos have figured out a way to do it, possibly because they're so much springier than everybody else, because even when they're going slow, they bounce incredibly. But I think fundamentally the dynamics is about the same. It's just we classify it very differently. And kangaroos physiologically, in their muscles, whatever, are very unique.
Well, of course, in Canada, we have this very interesting deer that I always get amazed when I see them. The deer that when they go fast, they hop on all four simultaneously. And when they run away, and I always thought that was very interesting that they naturally do that.
So that's a very interesting gait. It's called a pronk, and it's very violent, and they use all four legs at the time.
Yeah.
And it's a energetically ineffective gait. It costs them a lot of energy to do that. And what they're doing is they're showing off that I've got so much energy that you better not try and chase me. And so when they're startled, they'll do that pronk to show that they're not injured or old or something. And that's when they startle them. That's when it's not when they're going fast.
Okay, interesting. Yeah, I always thought that was
Animals show off.
Yeah.
Yeah, they're trying to show off, and we've got lots of things like the Eastern European dances that they do, all the acrobatics, etc., that are meant to demonstrate their athletic prowess to attract mates and say I'm strong and healthy, right? But those aren't cost-effective gaits, many of those dances.
Any final questions, comments?
John, I recorded the very first steps of newborn lambs. I instrumented some lambs as fetuses, put them back in the uterus, and then when they were delivered, recorded, because they're up and walking very quickly. So we recorded their gait in the first steps they ever took. And essentially they were adult gaits. There was nothing learnt in that gait. It made me wonder whether, well, I suppose this was a walking gait in sheep, but the fundamentals of the gait seem to be locked in at birth. And I wondered whether it was like those little things you used to get in the cereal packets that with a certain construction, you let it walk down a ruler.
So those ones are passive dynamic walkers, and they use the dynamics to walk. And sometimes I use a video from Andy Ruina's lab where he has a passive dynamic walker that walks and looks just like a little person without a body on it, and it walks and has all the characteristics with the swinging of the legs, the arms go alternatively. It has that twisting on the ball of your foot that wears out that coin-shaped thing in your shoes when they're old, with no motors and no actuators and no controls. It's powered by a very slight slope. And what he was trying to do was find a walking system that used the least amount of energy. And he did it in silico first, and then he thought, nobody's going to believe, he's going to think we did tricks or something. So then he did a physical model, and it worked. When I saw that, I started calling it Lucy, and the engineers thought it was because the joints were all loose, but it looked like a little Australopithecine to me. And it was the one that inspired me to start with this work, because it was so much, it had so many characteristics of human locomotion, human walking in it, but that was the best solution. They didn't try and make a little person. They tried to make an effective bipedal walking machine. And it turned out to have many characteristics that we exploit. And so what I've been trying to do is figure out how does those dynamics fit with what we're doing, rather than say, okay, what muscles do what and where are they going and things like that. But for the audience, Rob mentioned using sheep, where he took them out of the placenta, did some experimental manipulation, and then put them back to develop. And that procedure is referred to as marsupializing, because marsupials develop in the pouch outside of the uterus, right?
Well, these were back in the uterus.
Yeah, you put them back, but if you take them out, you put them back, it's called marsupializing.
So, yeah, so they just had, their gait was adult gait.
Yeah, so it would be interesting to find out how pre-programmed that is. And the only way you could know is to change the environment. So have them on the moon or something like that. Would they walk the same way? And I think, we haven't done this, but my suspicion is for the same reasons that people would run on the moon instead of walk, that four-legged animals would trot on the moon instead of walk. And then you'd find out whether a newborn sheep spontaneously walked or trotted. But I once wrote a book, and one of the chapters was, would a horse on the moon gallop? And that started the point of it was rounding off the book. The point was that at this day and age, we should understand the dynamics of walking and running and galloping and all these things, but a lot of it is a mystery, and it shouldn't be that way. In some regards, I think it's because we haven't been looking at this stuff, which is the foundation of what all the other muscles and nervous coordination and everything are doing. And that question was asked me when I participated in a kids camp here at Calgary, and I did a presentation on basically the same stuff I've been telling you about, only I did galloping and things like that. And this 11-year-old asked me, would a horse on the moon gallop? And I had to say, damned if I know, and I'm supposed to know,
Okay, let's thank John for his presentation.
Thank you.